Great. Well, welcome everybody to CC Colloquium for April 7th, 2021. And today we are doing something a little different. We're having a panel presentation about the Perseverance rover and Mars 2020 mission with some of our homegrown CC as well experts, as well as friends from JPL in this case. Steve Ruff is going to moderate this panel. And the idea here briefly is we'll have presentations and then lots of Q&A in which lots of time for Q&A, hopefully, from those of you who are here with our panel. So without any further ado, I gather there's no announcements. Well, Minnie's actually here on the panel, so if there are any announcements, she can sneak them in before the hour is out. So I'm going to turn this over to Steve to moderate our discussion. Steve?
Great. Thanks, Ariel, and thanks for everyone showing up. We're going to do 3 different presentations from each of our speakers, one from each, and it's going to sort of be in a kind of past, present, and future mode here, where we'll start with how Perseverance got to the surface of Mars successfully, then why it went there, geologically and sort of astrobiology science-wise, among other things, and then we'll end with where it's going to be going, kind of both on Mars and down the road. So that's the setup here. We're going to start with an outside guest, Aaron Sahura. He is the Deputy Phase Lead for Entry, Descent, and Landing for the Mars 2020 mission, aka Perseverance. He's from the Jet Propulsion Lab in California. And over the past decade, he's held a variety of roles on Mars, including Mars Science Laboratory, aka Curiosity, and the Mars 2020 project. And this includes leading the infusion efforts for terrain relative navigation technology, which he'll probably talk a little bit about. And he's got a bachelor's and a master's degree from Cornell University. And we just learned moments ago that he was on hand back when Jim was at Cornell, and we used to allow students and others to come and listen in on the Spirit Opportunity planning. He was one of those students listening in and watching along, and now he's moved on to become a part of his own rover mission, which is really exciting. So without further ado, we'll let Aaron take it away.
Hey, Steve, thanks a lot. Yeah, like Steve said, back in the day at Cornell, I had the privilege to see what was going on with the Spirit and Opportunity rovers. And it made me say, this Mars exploration thing sounds pretty cool. So let me share my screen and go into slideshow mode here. All right. So again, my name is Aaron Stehura. I guess I should say, the Deputy Phase Lead for Entry, Descent, and Landing on the Mars 2020 mission. So as most of you probably know, the Perseverance rover landed successfully on Mars on February 18th, but it was a long road to get there. So I'm going to tell you a little bit about the history and what it took to get us there before I turn it over to the other panelists. So just at a high level, this is kind of an overview of all different Mars missions that we've sent since the mid-90s until almost today. There's a couple of things missing. InSight is missing here. And of course, we've got a follow-on mission to the Perseverance rover now that we'll talk about at the end of this panel discussion. But the goals of NASA in exploring Mars have continued to advance. And we've continued to need more and more complex missions to answer the scientific questions about Mars that we are curious about. So specifically with respect to roving, we have a family portrait here that you can see on the screen now of all of the different rover sizes that we've sent to Mars, starting in the lower left with Sojourner in 1997. This is the first rover that we sent to Mars. It was about the size of a toaster oven. And that was followed by Spirit and Opportunity, twin rovers that were sent in 2004. And then the Curiosity rover, much larger, much more capable, that was sent in 2012. So to give everyone an idea, the Perseverance rover that we just landed on Mars looks a lot like Curiosity, but it's heavier and even more capable. And you don't have a great sense of scale here, but this image really drives it home for me. As we increase capability and complexity of these rovers that we're sending to Mars to give us more and more rich data sets, the size increases. And you can see here a model of the Curiosity rover compared to a Mini Cooper. So, what does this mean for me? This means that I have to land something the size of a car on Mars, and that's no easy task. So what you're seeing now on the screen on the right is a model of the entire spacecraft. The rover is this piece. You can see its wheels all folded up here at the bottom, and all of the equipment that we need to support the rover on its journey to Mars. And on the left, you see an actual photo that was taken at Kennedy Space Center early in 2020 before Perseverance launched. So what are we seeing here? If we go from the top of this, we have the cruise stage. That's this donut-shaped piece of machinery up here. It helps keep us alive, keep us warm, guide our trajectory, and give us power on the way to Mars. So there are solar panels on here, and there are a set of thrusters and some other equipment. Going down from there, we have what we call the back shell. And when you combine that with this piece on the bottom here, this thing we call the heat shield, those things connect together. They make up the protective capsule that protects the rover as it's making its dangerous journey through the Martian atmosphere during the process of landing. And finally, we have what we call the descent stage, or sky crane here. And this is what we sometimes refer to as our rocket-powered jetpack. So after, I'll talk more about the process of enter, descent, and landing in a minute. But the primary features that we can pick out on the descent stage is this set of 8 thrusters. And just like I said, it's a rocket-powered jetpack. So those thrusters allow us to slow down the rover, lower the rover down beneath the descent stage, and set the rover gently on the surface of Mars before we cut this thing away and crash it a safe distance away from the rover. So on the left here, you're seeing all those components midway through the stacking process as we get the spacecraft ready to put on the rocket and launch to Mars. I do want to point out, you can see here at the bottom of the rover, there's this black debris shield here. Underneath that debris shield is the Mars helicopter called Ingenuity. And you may have seen in the news recently, we just dropped that helicopter off on the surface of Mars, and it's about to make its first flight attempt. And this is the first time we've ever flown a helicopter on another planet. So it's a very exciting thing coming up. So this next image that we're looking at, on the left and right sides, you're seeing the halves of the rocket fairing. And this is the protective nose cone that goes over our spacecraft. And in the middle, you see the fully buttoned up spacecraft that we were just looking at on the previous slide, all ready to get encapsulated before we launch. So last July, in July of 2020, we embarked on our 7-month journey. So I like to say that, it took us 7 years and 7 months for 7 minutes of terror. And I'm going to explain a little bit more about what that means in a minute. But on this day when we launched, we embarked on our 7-month journey to Mars. That was almost 300 million miles overall distance covered by the rover. or covered by the spacecraft. So where were we going? We're going to a place called Jezero Crater. There was a landing site selection process that happened over several years before we launched to pick the landing site that we were aiming for. And the scientific community decided that they wanted us to head to this site called Jezero Crater. You can see the crater rim over here on the left side of the image. And the circle is roughly what we call our landing ellipse. So when we land on Mars, there's always some uncertainty on exactly where we're going to touch down. After traveling 300 million miles, there's a lot of uncertainty involved in getting to an exact point on the surface of Mars. And so, we have to pick an area that we know we're capable of landing in. For Perseverance, that was different. We were in a situation where the geologists that were guiding our landing site selection were interested in more and more dangerous areas. And by dangerous, I mean areas that had terrain hazards, large rocks, cliffs, things like that, that are not friendly to landing a spacecraft on Mars. And so we had to pursue some additional technology that would allow us to land in these new spots. I'm going to talk a little bit more about that in a minute. One of those technologies was called range trigger. And this was the capability for us to deploy our parachute that slows us down as we travel through the atmosphere of Mars, based on how close we were to the target. Previous missions did not use this method, and you can see a comparison back from Mars Pathfinder here at the bottom, Phoenix and Insight, another set of landers, and then the Curiosity rover that landed in 2012. You can see their possible landing ellipses. So these were the areas that those missions had to ensure that were safe and free of hazards. For Perseverance, because of this new range trigger technology that we were using, we were able to shrink that down dramatically, and that opened up a lot of different and interesting places to explore on Mars. So just to give everyone an idea of what it takes to land something safely on Mars, this process, we call it the 7 minutes of terror. So this is where my 7-minute comment came from earlier, because it takes about 7 minutes from the time we hit the top of the atmosphere on Mars until we make it through the atmosphere and set the rover safely down on the surface of Mars. And there's no way for us to actively control the motions of the spacecraft as it's traveling through the atmosphere. So we need to program it to do this all by itself without any type of human intervention. So we spend years and years testing bits and pieces of this process and convincing ourselves that the spacecraft can do what it needs to do to get down to the surface of Mars. So just a few highlights here. As we hit the atmosphere of Mars, we experience a lot of friction, and as the spacecraft slows down, and that heat shield on the front of the spacecraft heats up to something around 1600 degrees Celsius. So that's about 3000 degrees Fahrenheit. And as we're slowing down, we pull just below 11 Earth Gs. So there's a lot of deceleration there. Once we slow down enough to deploy our supersonic parachute, we deploy the parachute. It's about 70 feet in diameter. And that allows us to slow down even more as we travel through the atmosphere. But we're still not going slow enough quite yet. It's at this point that we get rid of the heat shield. So we deploy the heat shield because we don't need its protection anymore. And once the bottom of the spacecraft is exposed to the surface of Mars, we start taking pictures of the ground. And this is where that terrain relative navigation technology that I mentioned earlier comes in. So we take pictures of Mars, we compare it to a map that we have on board, and this tells us exactly where we are with respect to our landing target. And that allows us to avoid hazards that we've identified ahead of time. So this was what I like to think of as the killer app for Perseverance's enter, descent, and landing. This is what opened up Jezero Crater as a viable landing site for us, because we could avoid those rock fields and cliffs and other things that were dangerous to the rover. So once we slow down more in the parachute, we light up our rocket-powered descent stage, come out of the back shell, continue to slow down, lower the rover on tethers, set it safely on the ground. And like I mentioned before, we cut the descent stage free and fly it a safe way away from the rover. So this is the process of enter, descent, and landing. This is 7 minutes of terror that I mentioned. So just to wrap up here, I don't want to take too much more time, but I want to share a couple images that we were able to gather as we came down through the atmosphere of Mars. This first one here is from the Lander Vision System camera. So this is the camera that we were taking pictures of the ground with to match up to that map that I mentioned. And this is one of the earlier images. You can see the dusty atmosphere of Mars, and you can see, looking out into the edge of space, because this was such a wide field of view camera. As we were coming down, the Mars Reconnaissance Orbiter spacecraft, which is an orbiter that goes around Mars, was able to snap a picture of us as we were making our way to our landing site. So this little circle down here is our eventual landing site. And above it, you can see in the magnified chunk here is our spacecraft in its capsule. And on top of that, you can see our inflated parachute. So this is as we were slowing down on the parachute. And one of the very unique things about this mission is that we took a set of cameras along with us. And I'm going to, I'll post a couple links in the chat after I stop talking here to some different videos from these cameras that we were able to take along with us. This was a technology demonstration, but we were able to take footage. What you're looking at now is a picture from the descent stage looking at the rover as we were lowering it and getting closer to the ground. So this is the first time we'd ever seen this before. We've never been able to observe this process on Mars in such high definition video fashion before. So it was quite exciting. When it was all said and done, you have what I like to call the crime scene photo. The Perseverance rover's landing site is down here in the lower middle of the image. The descent stage, after it flew away, landed over here up and to the left. The parachute and back shell landed over all the way here to the left after we cut it off. And of course, the heat shield that I mentioned we got rid of on our descent ended up over here on the right. So, this is a picture of a job well done. That now all of my hardware is splayed across different parts of Mars, but the rover was safe and sound, and the touchdown was flawless. Of course, this doesn't happen without a big team of people. There's a circle around me, but surrounding me here, this is earlier on landing day on February 18th. This is a big part of the enter, descent, and landing team who worked on this project for years to make this possible. So with that, I'll wrap up and say thanks and pass it on.
Great, thanks, Aaron. So yeah, what we're going to do here is we'll do questions all at the end. If folks want to enter questions into the Q&A box, don't use the chat, but you can start putting stuff in the Q&A if you'd like, or you can wait till later. So we'll continue on with the current, which includes in part why we went there. So our own Jim Bell, who doesn't really need much introduction, but I will introduce him as a Mars photographer. And he, I think, appreciates that title and has been a Mars photographer for a long time with instruments that he's either helped to build or helped to operate. So Jim, take it away.
Thanks, Steve. Can you hear me okay and see my slides?
Yep.
Okay, great. Thank you. And Aaron, great. Thanks for the ride, man. I mean, awesome. You and the entire team, just some absolutely spectacular engineering, and got us safe to the surface. So let me just try to quickly go through some highlights. And of course, why did we go? What's the goal of the mission? The mission was born very shortly after Curiosity rover landed in 2012, and born partly of the realization that there were a lot of spare parts left over from Curiosity, and a new rover could be built using a lot of those spare parts for much less than it costs to build Curiosity from scratch. So the mission was born that way, but it was also born out of the Planetary Decadal Survey's primary goal for the current decade that we're in of starting a Mars sample return mission. So these are the main goals of the Mars 2020 mission. The rover is called Perseverance, but the mission is called Mars 2020. We explore the geology of a landing site, talk more about that in a moment, study habitability and potential biosignatures, evidence of potential past life on Mars that might still be preserved in a well-chosen landing site. And then the steps that sort of go beyond what Curiosity and earlier missions were able to do, prepare a returnable set of samples, 20, 30 or more samples that could come back as part of this round trip. And there've been 47 missions launched to Mars since 1960, and this is the first one that is designed to bring some parts of it back. And so that's what separates Perseverance and Mars 2020 from all other previous Mars missions. And of course, prepare for human exploration, meteorology, other kinds of tech demo and resource experiments, et cetera. So those are the main goals of the mission, and those colored our choice of the landing site. So Aaron talked a little bit about Jezero, just put it in context. Those of you who might know Mars from the world of telescopes might recognize Syrtis Major, the big famous dark feature on one hemisphere of Mars. And there's a big impact basin called Isidis right next to this volcanic complex here. And Jezero is just a little crater here on the edge of the Isidis impact basin. And the cool thing about it from a geologic perspective is that it was definitely a crater lake at one point in time. There's an inlet valley where water flowed down from the highlands, the ancient highlands to the west, ponded in the crater, and an outflow channel on the eastern side. And of course, the focus here is this beautiful fan-shaped deltaic deposit on the eastern side of the crater. There's a number of fans and fan-shaped deposits that enter the crater from a variety of inlets. This is the best preserved of them, and here's a view from a combination of spacecraft, including the European Space Agency's orbiter. This is our target. Pretty compelling geology telling us about the past flow of liquid water in a sedimentary environment, deposition, shallow water, shallow lake environment, maybe ice covered, maybe not, don't know, but a gentle depositional environment where sediments could potentially preserve evidence of ancient biosignatures from that area or from coming down from the highlands. The more ancient highlands to the west. So very compelling kind of landing site. Basic mapping told us, there's a delta there. There's crater floor deposits. There's carbonates in these marginal deposits. There's other kinds of interesting minerals in the deposits from orbit in the crater rim, and then a whole other panoply of interesting morphologies and mineralogies in the ancient highlands. So a really kind of a rich area to study, but a small area. You saw that in Aaron's presentation, and so we really pushed that team to get us to this special spot. And that's also unprecedented capability now that can be used for future missions to go to these really special small places out on Mars. So that's pretty cool. The rover itself has a competitively selected science payload and some other tech demos that it carries. So we run the Mastcam Z cameras, of course, from ASU. We were, along with 6 other science instruments, selected from the competition back in 2014. So we've been spending 7 years also, Aaron, working on the science instrument side, putting things together. Of course, the cameras were PowerPoint and CAD cameras for years. They didn't become real until just a few years ago. But there you can see there's other kinds of instruments, a weather station, several spectrometers on the arm, a ground penetrating radar, an oxygen producing tech demo experiment called MOXIE, and of course the Ingenuity helicopter drone tech demo, which has been the focus of the mission recently and will be for the next month or so. So we're doing a lot of camera work here. I'll talk mostly about the cameras and very quickly about what we're doing on them. Perseverance carries or carried 25 cameras. It's the most camera-rich mission ever sent out into deep space. 25, including the 2 on the helicopter, including some on the back shell and on the rover, looking up at the entry, descent, and landing equipment. And please check out those movies if you haven't. They're absolutely spectacular. And of course, you know, from a PR perspective, amazing, but also just giving the engineers all kinds of detailed technical information on how that system performed. But we run the cameras up on the mast, and there's a nice selfie that we just got down yesterday, in fact, with the camera on the arm. Took a selfie of the mast and the helicopter and other components. But we've been, as I mentioned, we've been working since 2014 on the design, on the documentation and review of the design, on the testing, on the prototyping, on the fabrication, on the calibration, on the development of the operations plans, etc. We've got an amazing operations team that work down in the fishbowl in ISTB4. For those of you who walk through that space and see a bunch of people hard at work on computer workstations and holding up models of cameras and stuff like that. Our downlink operations team, that's their base of operations. So that's great to use that facility in ISTB4 to do that. We work also very closely with the team at Malin Space Sciences, a small company in San Diego that builds deep space cameras. They built the visible part of Phil Christensen's Odyssey Themis camera. Hey, happy birthday, Odyssey, 20 years. It's awesome. They built the LRO cameras along with Mark Robinson and his team. They're building new cameras for Mark. They're helping us build our Psyche cameras. So we have an amazing relationship with MS Cubed in San Diego that goes way back. And it's been just great collaboration working with them. They're doing our uplink operations, while we're doing the downlink operations on campus. Cameras have calibration targets. They have electronics inside the rover. I won't go into this in too much detail. I can point you to some research papers you can look at. And we're doing both science and operations. We're doing all the geology one might expect, the imaging of textures, geologic context, morphologies, as well as color imaging, including some near-infrared color imaging for composition, mineralogy constraints. But we're also helping the rover drivers, helping the rover arm operators, helping the other instruments with the positioning and context of their instruments. So it's really a great science and operations collaboration that we're involved with. I won't go through all these, but just what have we been doing? It's happy Sol 47. It's the morning of Sol 47 today. We landed on February 18th. We spent a whole bunch of this early phase of the mission just checking things out, making sure all of our systems work, our zoom, our focus, our filters. We're getting the image quality we expected. We can calibrate the cameras in the environment that they were designed to operate in, testing our pre-flight calibration assumptions, developing new calibration parameters, and of course, doing the sort of initial science observations. Our first shots got this beautiful calibration target, which allows us to get the colors right. We saw a little Mars there. And then we also checked out the zoom capability very quickly. So this is looking right down in front of the rover, the closest point on the ground, and we're able to resolve grains sort of the millimeter at the millimeter scale. And of course, we're getting all of that in stereo as well. And then just a couple of days after landing, we exercised the mast capability. So we're mounted on that mast that I showed you the picture of, 360 degrees around, plus or minus 90. And we took a series of pictures at our relatively low zoom setting, 34 millimeter focal length, of an entire 360 going from the rover, including the deck of the rover, out to the horizon. So just shy of about 150 images in stereo of this terrain. And the raw data went out on the website relatively quickly, and a bunch of amateurs have turned this into Oculus VR and all that. It's great, all the stuff that that they're doing with this. You can see the scour marks from the retro rockets that Aaron talked about coming down onto the surface. So definitely we made an impact, a gentle one on this environment. You can't really tell the resolution in that panorama on the screen. It's downsampled dramatically, but here's just an example of one of these features in there. A half-meter or so rock that was dubbed the harbor seal because it kind of is wind-carved, vent-affected rock surface. We're taking the 3D data all the time. We can match the focal lengths on these zoom cameras from wide angle all the way to telephoto. And so we use those 3D images to develop digital terrain models of the landscape for geologic assessment, topographic assessment, as well as the models that are helping will eventually be helping the rover drivers and arm operators position onto the surface. And then very quickly after that Sol 3 kind of low resolution panorama, we fired up the zoom on both eyes at high resolution. And here we just get a very small part of the field of view. It takes many, many hundreds of images to go around. So we just did one sweep around as a demo of the zoom capability. And here we finally start seeing the delta from the ground. We're seeing the front edge of those beautiful deltaic deposits, and you can see that they're capped by some more resistant materials. There's a lot of what geologists would call scree, sort of landslide, fine grain material that's coming off of those slopes. But these are really important pictures for us to start doing the reconnaissance and figuring out how to get over to study those delta materials and get onto those delta materials eventually. Lots of puzzles, lots of questions. We haven't figured it out. And here's just an example. We see these layers. Is this a slump block that's come off of the capping material? Are these foreset beds in deltaic deposits that the lacustrine geologists out there will know all about? We need to get closer. We will get closer to these and other materials, and some of them will be doing direct sampling of them in situ. So that's exciting too. Lately, we've been focusing on the helicopter. That's the phase we're in right now. And so we've been hunting for places to park the rover while the helicopter takes its flights. And this is exploiting some of our color capabilities to make these garish Andy Warhol kind of false color composites that really exaggerate color, bring out subtle color differences, and allow us to focus on color difference as a proxy for composition or mineralogy differences, helping guide the other instruments that do the actual spectroscopy. So that's pretty cool. But we'll be parking somewhere in here, probably right about where my cursor is. In the coming days, we'll be 50 to 60 meters away from the helicopter as it does its flights. And we'll be using the Mastcam Z cameras to take movies of those helicopter flights. Those of you on Twitter or Facebook have seen this. This came down last night. This is our first selfie of Perseverance taken with the camera on the arm, the Watson camera, which is just like the Molly camera on Curiosity. And of course, we have a buddy. We have a selfie buddy here, the Ingenuity helicopter. We were able to take some high-res images yesterday that came down yesterday with the Mastcam Zs. The engineers are really interested in the latches and the solar panels and doing kind of engineering diagnostics. So we're zooming in tight to get these pictures for the engineers. So starting potentially as early as this weekend, well, actually the next few days, we're doing some tests of our video capability. The engineers are doing some tests of releasing these latches and doing a low speed spin of the rotors without taking off. We'll start driving away towards that parking spot that I identified earlier. And then potentially as early as this weekend, we'll fire it up and take those images and movies. The Mastcam Z is the only camera that can both do video on the rover and has the high resolution zoom capability needed to see the helicopter from the range that the engineers and managers think is safe, just in case the thing goes out of control. We don't want it crashing into the rover itself. So that's why we have to back off to that distance. But it's going to be fun, and we've got a huge responsibility as part of this really historic aviation first. So we're we're looking forward to it. We're exhausted, but we're looking forward to it. So that's going to be a lot of fun. And then this is kind of a prelude into what Minnie's going to talk about. Of course, we are #1 here, the first part of that decadal survey highest priority Mars sample return mission. I know Aaron's working on the second part already at JPL and elsewhere, thinking about that fetch rover that's going to capture the samples that we eventually start collecting after the helicopter phase is over. And then this follow-on missions will get them into Mars orbit, bring them back to Earth, and hopefully we'll be studying them in laboratories on campus, including laboratories of our CC director, hopefully. So that's all I've got there, Steve.
Great, thanks, Jim. That is a nice setup for Minnie. And we'll have to see all of the cool stuff that is coming from this camera and the other cameras as well. So we have to give a little nod to Watson, for example. So that was big of you to put that up there. All right, so next up is our CC director, Minnie Wadhwa, who, in addition to being a cosmochemist who studies rocks from space, she was recently part of an independent review board that NASA convened to look at this big, sort of very challenging and expensive effort to return samples, and they wanted input from outsiders to kind of make sure they're on the right path. So, I wanted Minnie to come on board and kind of present some of that stuff, or at least, the flavor of that today. So take it away, Minnie.
All right, thanks a lot, Steve. So I'm gonna try not to take too much time. I know there's, I want to leave plenty of time for questions here. So as Jim already talked about, the fact that Mars sample return was the highest priority flagship mission from the last decadal. So, the Mars community, or actually broadly the planetary science community, there was a very strong feeling that, the next step in Mars exploration, really in terms of making a big difference in our understanding of questions regarding habitability, as well as geologic evolution of the planet, all of that could be addressed best by returning samples, and not just any samples, but well-characterized, scientifically selected samples from Mars. And here are just sort of some quotes from that decadal report that highlight the importance of this particular mission. And the MAX-C, reference to MAX-C, by the way, used to be Mars 2020, used to be referred to as the Mars Astrobiology Explorer Cacher, it's now called Mars 2020. So that's the reference there. But essentially, bottom line is that, the feeling was that Mars science had reached a level of sophistication such that fundamental advances in basically answering the most important questions would only come from return samples. And so that was the sense. And then most recently, actually, about 3 years ago, I was part of this group called IMOST, which is International MSR Objectives and Samples Team, acronym within an acronym right there, which is so totally NASA. But anyway, this is the group that identified essentially 7 high-level goals for Mars sample return, and encompassed all of the things that you can think about as being important for Mars in terms of understanding geologic processes and history, the biological history of Mars, evolutionary timeline for the planet as a whole, inventory of volatiles on the planet, the origin modification of the interior, so the evolution of the mantle and core and the interior of the planet through analyses of isotopic geochemical characteristics of the samples. Understanding also environmental hazards, and this would be relative to future human exploration that's anticipated to come soon thereafter. And also from the perspective of in situ resource reutilization aspect of things as well, also relevant to future human exploration. So those are sort of 7 high-level goals. And then, Mars 2020, of course, is, as Jim said, the first stage in sample return. And the goal, of course, we heard about kind of the landing site here, which is this Paleo Lake environment. And on this map, which sort of has a nice sort of illustration of all of the different landing sites of previous missions, And of course, the Tianwen lander from China that's expected to be landing in 2020 as well. So relative to that, our Mars 2020 landing site here will give us an opportunity it's expected within the first sort of Mars sol, or about 687 Earth days. That's going to be the duration of the prime mission, during which the sampling is expected to be conducted primarily within Jezero crater. And as we know, all of these missions that have been exploring the rover missions that have been exploring Mars, Spirit, Opportunity, and then Curiosity, they've all extended well beyond their prime mission lifetimes. And so the hope is that Perseverance is going to do the same. And so the expectation and the hope, and I very much hope so, is that there's going to be an extended mission where there'll be collection out beyond Jezero, perhaps in a site called Midway, and that'll expand very much more the types of samples that we might also get. I just wanted to say really quickly about the sample tubes that are aboard Perseverance. There's about 43 of them, and 38 of them can basically accommodate rocks and regolith, and an atmosphere sample too, actually, in the headspace that's going to be in these tubes. And just to sort of show you a picture here of these, I can talk about it later if you would like, but there's, these are hermetically sealed sample tubes that hopefully will preserve the sample for a number of years until they can be picked up. And so the Mars sample return campaign, as it's referred to, which starts basically with Mars 2020 and ends at the sample receiving facility on Earth, that whole campaign has multiple mission elements. And so the first part of that is, of course, Mars 2020, which of course will be doing all of these things, landing in, it's already done that, landed in Jezero crater. It'll be exploring and characterizing the materials there. It'll collect samples for future return. It's going to retain some of those samples on board and deposit some in a cache. So we don't know the detailed plans at this point, but the expectation is that there will be a depot that'll be created, and there may be some samples that'll be retained on board. And it'll have the capacity to actually deliver some of those retained samples back to the sample retrieval lander, which is the second component that's shown here. And that is going to land in the proximity of Jezero crater, potentially close to one of the depots that's going to be prepared by Mars 2020. It'll deploy a sample fetch rover to retrieve the samples from the depot. And then the samples are going to be basically transferred over to an orbiting sample container within the Mars Ascent vehicle that's part of the sample retrieval lander. And then the MAV is going to launch the OS into a stable low Mars orbit. And then the third component is the Earth return orbiter. And this is actually a component that's going to be delivered by ESA. So this is a collaboration, by the way, the whole campaign is a collaboration between NASA and ESA, with ESA doing about a third of the work that's required for this whole thing. And so the Earth return orbiter, and again, sort of notional launch dates for each of these are noted here, 2026 for these. And so the Earth return orbiter is going to be delivering the NASA supplied capture, containment, and return system. And this is going to basically satisfy planetary protection requirements, which is essentially going to be breaking the chain of contact with Mars. And of course, it'll provide relay support for assets on the ground. It's going to capture the orbiting sample in low Mars orbit. And after capturing that sample, it's going to return that orbiting sample container via the Earth entry vehicle back to Earth in the Utah Test and Training Range. So that's where it's expected to come down. And so those are sort of the different elements, and actually how this fits together in terms of a broader architecture for the whole kind of Mars sample return campaign. As I mentioned, the whole campaign is comprised of, starting with Mars 2020 and then going to the sample receiving facility on Earth eventually. And it's relatively complex. I'm not a huge fan of this particular graphic. It's a little confusing. I mean, so you've got Earth down here, you've got Mars up here, and you've got, of course, Mars 2020, that's on Mars. There will be a couple of these launches of the Earth return orbiter and the sample retrieval lander, which is then going to send the orbiting sample up to the ERO, and eventually you will have the orbiting sample container that's going to come back in the Earth return vehicle. And I just wanted to kind of, it's a little bit clearer actually in this little video, which is without sound, but this is a video that shows kind of some of the timeline of some of these missions and the plans for the sample return. And we can watch this. And if you want to start the questions, we can, Steve. I don't want to cut into too much of the time for that, but it's kind of an interesting video that was shared last year at the MEPAG meeting by Jim Watson. That sort of shows all of these components put together.
Cool. Okay, so is this the last thing you were going to show?
Yep.
Okay. All right. So yeah, maybe we'll take advantage of that and go on to some questions, and please keep that playing, Minnie. It is cool. So there's been a couple already addressed. Let's at least go to new ones. It looks like Jim is going to answer a question about from Aaron Alexander about how can age and weathering be identified in the deltaic deposits using Perseverance's instruments. So Jim, are you available?
Yeah, can you hear me?
Yep.
Okay, that's a great question. Of course, we can't do absolute age on this particular vehicle. We can do relative age. We know from orbit where we're driving around and what the impact crater density is in those areas, and all we can see layers in the stratigraphy. You saw some layers in some of the pictures I showed, so we know that the materials underneath are older than the materials up above, assuming the layers are relatively horizontal, which they seem to be. And so we can do relative age dating, but to do the absolute radiometric age dating, we have to bring the samples back, and Minnie is going to do that work. She is committed to doing that work, or Minnie's graduate students 10 years from now are going to do that work. And so that's one of the most important reasons to bring the samples back. On the science definition team that Steve and I both served on for this mission before it was formulated, one of the most important things that came out of that work was, we want to study sedimentary aqueous deposit, all that kind of, but we need some fundamental knowledge about the age of these materials to be able to tie the crater record to absolute age dates from radioactive age dating, like we've done on the moon. So we want to take that leap for Mars. That means bringing the samples back. And then the weathering, there we can use the chemistry, the mineralogy, the imaging. We can see weathering rinds, we can see veins at other landing sites. We can see, evidence of aqueous alteration in the mineralogy, clays, sulfates, carbonates, etc. Generally, the cameras aren't doing that. These are cameras, not spectrometers, but of course we're helping to define the observations, do the triage of the landing site and our traverse path that will guide the other instruments. Very sensitive and can generally only observe very small regions at a time. So they need the triage of the imagers, all the imagers on the vehicle to guide that selection. And we haven't done much of that yet. It's still early days on this mission. And many of those detailed instruments, especially the ones on the arm that'll do a lot of the chemical and mineral work, are still being checked out and calibrated.
That's great. Thanks, Jim. Here's one for, probably Jim from Paris. How has the landing site selection process or strategy changed over the many rover landing missions on Mars?
Yeah, I'm sure Aaron could dive into that too. In fact, if you'd rather take it, Aaron.
Well, yeah, let me just start.
Go ahead. Yep.
Certainly from I can speak from an engineering standpoint, because that's of course my role on these projects. But the process is, it's driven by science. So this process is always a multi-workshop format where there are landing site workshops that are open to the public. Members of the scientific community obviously can come from all over, as well as observers. And we bring an engineering team to those venues as well. We try to get a sense of the places that the scientists want to go at the initial early workshops. And then on the engineering side, we take that information and we go and delve deeper into the possible candidate, into the candidate landing sites. And we look at, what altitude is the site at? How dangerous is the terrain? What does the traversability story look like? Is the rover actually going to be able to, move around effectively once it gets there? So we try to come up with initial answers for those questions, and we converse back and forth with the scientists, and say, is it even possible for us to go to these places? So one of the big differences for 2020 is that I would say it's the first mission where engineering wasn't a major limiting factor. For all the previous missions, we kind of pejoratively say, oh, we had to land in a parking lot because we were so concerned for the engineering safety. And that wasn't the case for this one. So, feel free to add on there from a science perspective, Jim.
No, that's exactly where I was going to go. We keep making unreasonable demands of you and your colleagues. We want to land anywhere we want on Mars. It's nothing short of that scientifically. Where do you want to go? Anywhere I want to go. Anywhere this group of us want to go. That's where we want. And then
we get to be the wet blanket and say,
and you guys get to be the guys and gals get to be the wet blanket, right? And so it was delightful in this case when it was like, yeah, we can do that. Oh, what about if we wanted to go right up to the delta? Yeah, we could do that. So it's like, great.
Yeah, what if you wanted to land on the delta?
You could do that too. Yep. So it really is getting more and more sophisticated, more and more accurate in terms of picking places to go. And of course, as the orbital assets continue to get better, and HiRISE and Themis and all these other instruments that have been operating up there and have in the past and give us better and better views, we're going to want to be more pinpoint in our accuracy in future missions. So it's just great.
Great, that was perfect. So we have a question from an anonymous attendee that may be for Minnie, which is, do the samples from Mars have the same planetary protection requirements as samples from asteroids like Bennu, for example?
Yeah, actually, no. So Mars sample return is categorized as what's called category 5, which means that they actually have to meet much more stringent planetary protection requirements. And so that's why basically the design of the return vehicle and the mechanism is such that it allows for that breaking the chain of contact, as they call it, with Mars. And so the sample is going to be returned, or the requirement is for it to be returned in a completely sealed container that basically there's not going to be any kind of Mars dust on the outside that's going to be kind of exposed to the Earth environment when it comes back. And then of course it'll be in a sample receiving facility where it will be assessed for any kind of potential hazard or evidence of any extant life maybe, or past life more likely. But that's the first order of business, is that it's going to have to be assessed for a potential, kind of biological hazard to the Earth environment. So yeah, so that's part of the planning process, is to see, how are we going to be able to handle that? So it has much more stringent requirements than an asteroidal sample return.
That's great. I've heard it said that these tubes were the cleanest objects ever sent into space. I think that's probably somewhat true.
Yeah, I believe that's, yeah.
Okay, so a question from someone who clearly knows their sedimentary geology. Will the fine-grained, Tim Demko, will the fine-grained distal/profundal facies of the coarse-grained littoral/foreset facies be examined first? So Jim, is there a sense of which part of the delta?
So it's a trap. So you're making a whole bunch of assumptions, Tim Demko. Is it really a delta? Are the distal deposits fine grained? Are they distal deposits, or were they part of a larger delta that has been eroded? Are those layers foresets? I mean, I can't answer any of that. Nobody knows the answers to any of these questions. They're spectacular questions, and we're all asking these questions, right? They're exactly the right questions, but we just don't know. We're too far away. We haven't been able to fire up the, the full power of this battle station to address these kinds of remote sensing and in situ questions. What we do know is that there are what appear to be distal remnants of the delta. It could be something else, but that's what they appear to be as one hypothesis, that are closer to us than the main body of the delta. What we also know is that we cannot go from our current location on a straight line path to the front cliff of the delta. We can't do that. There's too many big sand dunes in the way. So we have to go around this big, really interesting area that's between us and the delta. We can't go into that. And so there are remnants to the clockwise direction. There are remnants in the counterclockwise direction. And there's kind of a brawl coming on the clockwise people versus the counterclockwise people, because there's all kinds of great stuff to see in both directions. Different kinds of materials to sample, different parts of the crater floor that could be sampled and cached in both directions, and really interesting putatively deltaic remnants in both directions. And so, the rover drivers are off looking very carefully at both possible traverse paths. The answer may come down to vehicle safety, or maybe not. It may just be a science brawl. In fact, we're having part of that brawl at our meeting at midnight tonight, since we're all on third shift Mars time. So this is a lot of fun, and these are great questions, and I have no clue to the answer yet, but we'll figure it out.
Good answer, no clue. All right, so I think we have time for one more, and there's one more in the...
There was one that I saw that rotated off about biosignatures. I don't know if you saw that one.
Oh, did it not get answered?
It did. I said I was going to answer it live, but then it disappeared.
Okay, what kind of so Addison Sherman, what kind of biosignatures are you looking for in the delta deposits?
Yeah, and that's a great question too. And Minnie mentioned potentially search for extant life, and so I mean technically, if there were something macroscopic that kind of walked in front of the camera, we would see it, right? And okay, that's one way to search. Technically, if there are fossils, whatever trilobites kind of equivalent dinosaur femur preserved in these sediments, we would see it. We'd see them. But realistically, none of us are expecting any of that, right? The fossil record on Earth didn't start till 550 million years ago or so, right? Before that, it's all soft-bodied, soft-shelled microorganisms and colonies of microorganisms. And that's the kind of model. We're looking at the Precambrian geology model of life on early Earth. And life on early Earth, most of the actual evidence of the bodies of those microbes and clusters of microbes don't exist anymore. They've been long eroded away. But many of the structures that they made, like stromatolites that was in that picture that I showed, the ones that are in Australia, Greenland, elsewhere around the world, in the ancient terrains of the Earth, those are the kinds of things that we might have the best odds of seeing, textural evidence. Now, there could be very subtle organic and isotopic evidence of those past life forms preserved in there, as happens in the Precambrian on the Earth. You have to take those samples from the Pilbara, from Greenland, from the Canadian Shield. You have to take them to the laboratory to do that. You can't figure that out in the field. And then there's big fights among Precambrian geologists about what's going on. Another reason why we have to bring these samples back. We got to carefully select them, look for those kinds of textures, fabrics, mineral evidence, chemical evidence, organic evidence, if we can detect any. Cache those samples, carefully store them, carefully go get them and bring them back to this planet, to Minnie's lab, and figure it out from there. I mean, we also look, I mean, and Steve knows this well, if we were to claim we found evidence for ancient life on Mars from a subtle, barely above the noise signal from instruments that are far less capable, spectacular instruments, but far less capable than those in the laboratory on the Earth. If we were to try to make that claim, nobody would believe us, right? Extraordinary claims require extraordinary evidence. So I think everybody realizes that the mission isn't done. Those claims aren't founded and validated until we bring the samples back.
Short of a dinosaur bone.
Short of a dinosaur bone, which I guarantee you would hear about.
You think so?
I think
All
so.
right. Okay, we're at the bottom of the hour, so maybe on that note, Ariel, anything you want to add?
No, I've got questions, but given the time, I think we should probably wrap this up.
Yeah, I had that same feeling.
So thank you, Aaron and Jim and Minnie. Thank you very, very much. That was really great. I'm hoping it's not the last time we do something kind of like this around an active mission. I think it's kind of fun to tap our expertise and expertise of our friends to bring this kind of thing to our CC community. So thank you very, very much.
Indeed.
And thanks, Steve, for moderating.
Of course. Yes, I appreciate all of the great presentations and Q&As.
Yeah,
Great.
questions.
And thank you all for attending.